Imagine spending, like, years building this state-of-the-art calculator. You meticulously wire the circuits, you design the sleek glass interface, you program the basic operations, addition, subtraction, multiplication.
Matches all the standard stuff you would expect.
Exactly. And the very first time you turn it on, instead of giving you a sum, it just starts translating 19th century French poetry into English.
I mean, you would probably assume you were losing your mind. Or, at the very least, that one of your engineers had played a really, really elaborate practical joke on you.
Because, well, tools are supposed to be bounded by the intentions of their designers. You build a calculator, it calculates. You build a car, it drives.
Yeah, they do what we tell them to.
But what happens when you build a software system and it suddenly starts doing things you literally never explicitly programmed it to do? Today, for you listening, we are unpacking a truly fascinating piece of tech history that kind of challenges everything we assume about how our tools work.
It really does turn that whole concept upside down.
We are diving into a long-form essay published today, May 30th, 2026, in Tech-Reader magazine. It's by Aaron Rose, and it's part 3 of a series titled How ChatGPT Was Built, the Capabilities Nobody Designed.
And it is just a remarkable piece of reporting. It takes us back to this specific, almost eerie moment in the history of GPT-3.
Eerie is definitely the right word for it.
Right. Because the engineers at OpenAI had built this massive server infrastructure. They trained the model, they scaled it up, and all the underlying math held together perfectly. I mean, the project was a massive technical success.
Everything was green lights.
Exactly. And then they sat down to evaluate what the system could actually do in practice.
And that is exactly when the unease set in, because they discovered the model possessed these profound abilities that nobody had actually put there.
None of the developers wrote code for it.
Right. And for you listening, we are all so used to the idea that the technology in our pockets or, on our desks only does what a human being explicitly told it to do in a string of code.
Yeah, line by line.
But this deep dive totally shatters that assumption. We are exploring what happens when engineering completely outpaces human understanding, and the creation just, surprises the creators.
To really grasp why this sent shockwaves through the tech world, we kind of have to look at the fundamental architecture of these models.
Let's do it.
So the researchers built what was, at its core, just a next token predictor. Its only job, literally the only objective function it was given, was to look at a sequence of words and guess the next word.
Like a giant autocomplete?
Essentially, yes. But by trying to get really, really good at that one simple guessing game, they ended up with something that behaved like a general reasoner.
Okay, let's unpack this. Because on the surface, guessing the next word sounds like, autocomplete on my smartphone. How do you get from an oversized autocomplete to a system that writes syntactically valid code in programming languages it was never explicitly taught?
It sounds impossible.
It does. Aaron Rose notes it was performing multi-step arithmetic, translating between rare language pairs, following these super complex conversational instructions. In normal software development, there is a very clear paper trail for those features. A product manager says, hey, we need a math module. An engineer writes the code, they commit it, and boom, the software does math.
Right, there's intentionality.
But there is zero provenance here. No one wrote an arithmetic function. So how does a model designed just to guess a word somehow teach itself math?
Well, it comes down to what is actually required to accurately predict human language. Language isn't just a random string of sounds, right? It's a compressed representation of reality.
Okay, what do you mean by that?
So, if I give the AI the sentence, Johnny has 5 apples, he gives 2 to Sarah, therefore the model has to predict the word 3.
Oh, I see. To guess 3, it can't just rely on grammar or spelling.
Exactly. It actually has to map the conceptual relationship of possessing an object, losing an object, and then calculating the numerical remainder.
Wow, so it has to actually understand the reality behind the words to win the guessing game.
Precisely. If a model is small, it might just guess a random number based on statistics. But to get highly accurate at predicting the next word across the entire internet, the model is basically forced to develop internal representations of logic, syntax, and mathematics.
That's wild.
It's not a calculator, but it learns the rules of arithmetic because those rules are embedded in the structure of the text it's trying to predict. And the crazy thing is, the only variable researchers changed to unlock this deep reasoning was scale.
They just made it bigger.
They made the model larger, and they trained it on more data. That gave rise to the whole phenomenon researchers dubbed emergent abilities.
Which brings us to the data itself, because there was a deeply strange graph shape associated with this emergence, wasn't there?
Oh, yeah, there was. When researchers evaluated a specific capability, say, multi-step math across models of increasing size, they didn't see a gradual learning curve at all.
Like it didn't just slowly get better over time.
Not at all. A small model with a few million parameters, and by parameters we just mean the artificial synaptic connections inside the network, would score near zero on the test.
Okay.
A larger model would also score near zero. A billion parameter model, still near zero. And then abruptly, at a specific threshold of scale, the capability would just materialize.
So if you plot that on a chart, you're looking at a flat line dragging along the bottom of the graph, and then just a sharp vertical spike.
Yep.
Nothing, nothing, nothing. Then suddenly, it knows how to do math.
That is the literal shape of emergence.
Yeah.
And according to Rosaseth, this consistently started happening around the threshold of 100 billion parameters.
100 billion?
Yeah. Below that massive scale, nothing. Cross that roughly 100 billion parameter mark, and the model suddenly understands how to balance a chemical equation or translate Swahili to English.
That total lack of provenance makes it sound like magic. I mean, it genuinely makes me wonder how any engineer had the confidence to keep pushing forward.
It is pretty daunting.
If you don't fully understand what's happening under the hood, how do you justify plugging in thousands of more servers and running the experiment again?
Well, it sounds reckless in a modern software context, for sure. But if you look at the broader history of science, this dynamic is actually the norm.
Wait, really?
Yeah, this situation where engineering outruns theoretical understanding has happened over and over again. People built working steam engines long before thermodynamics existed as a formal academic discipline.
Oh, I love the historical analogies Aaron Rose uses here to ground this.
The steam engine is the perfect parallel. Tinkerers and engineers were just trying to pump water out of coal mines. They experimented, they minimized pressure leaks, they got the machines working.
Trial and error.
Exactly. The formal mathematics of entropy, heat transfer, and energy conservation took decades to catch up. The engines powered the Industrial Revolution before scientists could fully explain why they worked.
And the same thing happened at Kitty Hawk. The Wright brothers flew airplanes before aerodynamics was completely mapped out.
Right, they just built it.
They didn't sit on the beach in North Carolina refusing to build a wing until they had a unified mathematical theory of lift. They built a wind tunnel, tested different shapes, and found what worked through empirical trial and error.
And in artificial intelligence, large language models follow that exact same historical pattern. The systems were advancing far faster than the theoretical science explaining them.
So they were basically observers to their own creation.
Yeah, the OpenAI researchers were making empirical observations, noting that, hey, this 10 billion parameter model fails at logic, but this 100 billion parameter model succeeds, before they had a principled mathematical account of the underlying mechanics. The engineering simply arrived before the explanation.
Here's where it gets really interesting, because I have to push back on this narrative of them being totally in the dark.
Okay, let's hear it.
For you listening, you might be thinking what I was thinking when reading this. Didn't the developers have scaling laws? I remember hearing that AI labs had mathematical formulas predicting that as you pump more compute and data into these models, they get smarter. So they weren't completely flying blind, were they?
That is a vital distinction to make, and it's a misconception Rose addresses directly. Yes, they had scaling laws. Those laws accurately predicted that the overall performance of the model would improve.
Right, so they knew it would get better.
They knew the model would get generally better at predicting the next word, and that the error rate, what engineers call loss curves, would smoothly go down. But, and this is the crux of the issue, those laws absolutely did not predict which specific capabilities would appear.
Oh, okay. That is a huge difference. They knew the overall intelligence, for lack of a better word, would go up, but they didn't know that specific scale X would unlock Python coding or scale Y would unlock advanced chemistry.
They had no idea. They didn't know which capabilities would appear, at what scale they would unlock, or why they would appear at that specific threshold. Those were entirely empirical discoveries made after the fact.
Wow.
Yeah, anyone claiming that the emergent abilities of large language models were fully mapped out and planned on a whiteboard is telling a story that is much tidier than the historical truth.
Which forces us to ask a really difficult question. How do we even physically conceptualize this? I mean, if the overall learning process is a smooth, predictable curve, how do we wrap our heads around a sudden, vertical leap in a specific skill? Yesterday, the AI couldn't do math, and today it can.
To visualize this, Rose introduces a framework from statistical physics. It's a phenomenon you encounter every single day but probably never think about.
Which is?
The freezing of water. Think about water sitting at 33 degrees Fahrenheit. It is a liquid. You
Okay.
drop the ambient temperature by just 1 degree to 32 degrees Fahrenheit and it becomes solid ice.
And the difference in temperature is completely continuous. A 1-degree drop is just one incremental step on a thermometer.
Yet the macroscopic behavior of that substance undergoes a complete, discrete transformation. There is no sudden jump in the underlying physics of the cooling process, but the liquid turns to a solid. Physicists call this a phase transition.
The phase transition.
Right. And the researchers evaluating these language models realized they were looking at something structurally identical.
Because during training, the models were constantly improving. The loss curves, that overall error rate we mentioned earlier, were dropping on a smooth, continuous diagonal line. There was no sudden spike in the underlying training metrics.
But the observable capabilities did spike. Just like water transitioning to ice, the underlying mathematical change was continuous, but the behavioral change was sudden and discrete.
That makes so much sense.
Yeah, framing emergence as a phase transition didn't magically explain the entire phenomenon, but it gave researchers a rigorous vocabulary borrowed from physics to talk about it, rather than just throwing their hands up and calling it spooky.
While the physics analogy is elegant, there's another analogy in the essay that I think captures the actual feeling of this much better, especially if you've ever watched a child grow up.
Oh, the reading analogy.
Yes. Think about a child learning to read. They spend months in what looks like total stagnation. To the kid, the letters on the page seem completely arbitrary. As a parent, you watch them struggle, and you might see zero progress week after week. The capability is flatlining.
Right, it seems like nothing is happening.
Exactly. And then one afternoon, something just shifts. The kid sits down and reads a full sentence aloud.
The capability appears to arrive fully formed, like overnight.
But logically, we know the child's brain wasn't idle during those 6 months of apparent confusion. The neural architecture in their head was making thousands of invisible micro-adjustments all along.
Synaptic connections were forming.
Visual patterns were being consolidated, yeah. The progress was continuous, we just couldn't measure it from the outside until it crossed the threshold of being functionally useful.
And that maps perfectly onto what is happening inside the neural network of an AI.
I also think about it like a city planner building a new town. You lay down a few roads and traffic flows fine. You keep building more roads, expanding the grid. You're just adding asphalt, a continuous increase in scale.
Right.
But eventually you hit a critical mass of interconnected streets and suddenly you get a traffic jam. You didn't explicitly design a traffic jam module. The traffic jam is an emergent property of the network reaching a specific scale and complexity.
That is a brilliant way to frame it. The continuous addition of roads, or in the AI's case, parameters and data, creates an environment where complex, unforeseen behaviors naturally emerge from the network.
It just happens.
Yeah. The loss curves show that continuous, invisible improvement during the training process. But our benchmark tests, the tools we use to ask the AI questions, just show stasis followed by sudden capability.
But hold on. If I'm a skeptic looking at this, and science demands rigorous skepticism, my first thought is that maybe the AI isn't suddenly experiencing a magical spark of intelligence. Maybe our testing tools are just flawed.
That is exactly where the scientific community went next.
Did anyone point that out? Was this sudden vertical leap actually real or just a mirage created by our benchmarks?
That exact question became the center of a fierce, highly technical debate beginning around 2023. And it's a debate we have to look at impartially, because both critics and the proponents had incredibly strong, valid arguments.
Okay, what were the critics saying?
Well, the critics looked at those sharp vertical graphs and argued that emergent abilities might just be an artifact of how humans measure success.
Meaning the tests themselves were creating the illusion of a leap?
Yes. They pointed out that most AI capability benchmarks are binary. They are pass-fail.
Yeah.
Think about a multiple-choice math test. The model either selects the right answer or it doesn't. So imagine the model's underlying capability to do math is actually improving continuously, just like the child learning to read. It goes from 49% accuracy, which is a failing grade, to 51% accuracy, which crosses the threshold into a passing grade.
Oh, if your benchmark only records the final binary outcome, pass or fail, that gradual 2% improvement looks like a sudden overnight leap.
Exactly.
To the spreadsheet, the capability appeared out of nowhere. But to the model, it was just one more incremental step.
Exactly the critic's point. To prove it, Researchers redesigned the tests. They switched to benchmarks that captured continuous improvement. Essentially, they started giving the AI partial credit for getting close to the right answer or measuring how confident the model was in its guesses.
And what happened? Did the sharp, spooky, vertical lines flatten out?
In many cases, yes. When measured with granular partial credit, the emergence of these skills looked much smoother. The vertical spike relaxed into a more gradual curve.
Which raises the million-dollar question. Does that mean emergent abilities are a myth? If the leap is just a measurement error, is the whole concept of sudden AI capability just hype?
What's fascinating here is that this is where the debate gets highly nuanced. Even though the mathematical curves flattened on paper when given partial credit, the practical reality for the user remained completely unchanged.
Oh, that makes sense. Because, like, partial credit doesn't help me if I need the AI to actually write a working piece of software for my business.
No, not at all.
It either compiles and runs or it crashes.
Precisely. A model that is 80% good at writing a Python script is often functionally useless to a programmer because a script with a 20% error rate just breaks.
Right, you can't use it.
So the capability only becomes useful enough to matter when it crosses a very high threshold of accuracy. So while the underlying mathematical development might be gradual, the utility of the model remains genuinely abrupt.
So the debate didn't debunk emergence, it just reframed it.
Yeah, the debate introduced a necessary epistemic caution. We have to be careful that we aren't confusing a change in our measuring stick with a change in nature. But regardless of whether the graph is a spike or a steep curve, the fact remains that incredibly powerful, undesigned capabilities were appearing at scale that were totally absent before.
So what does this all mean? Whether it's a sudden phase transition like water freezing or a steep continuous curve like a child learning to read, the end result is exactly the same. We have systems operating in the real world with skills their creators did not intentionally put there.
It's a paradigm shift.
And Aaron Rose argues this fundamentally changes the story of technology itself.
It permanently breaks what Rose calls the standard chain of intentionality.
The chain of intentionality. Someone decides what software should do, an engineer builds it to do that specific thing, and the resulting tool reflects the builder's intent. But emergence severs that chain entirely.
Exactly. Nobody at OpenAI decided GPT-3 should be able to write code, but it did.
That is just wild to think about.
And if we connect this to the bigger picture, this broken chain of intentionality is precisely why the alignment problem has become the most urgent conversation in technology today.
The alignment problem being the incredibly complex challenge of making sure AI systems behave safely, ethically, and beneficially for humanity.
It is hard enough to align a system with human values when you know exactly how it works. But how do you guarantee a system is safe when you don't even know its full capability space?
Capability space.
That is the term researchers use for the complete boundary of what a model can and cannot do. During training, the models use a mathematical process called gradient descent.
Right.
It's basically tweaking billions of internal dials over and over to minimize errors and find the most efficient way to predict text. We know gradient descent works, but we don't know what hidden skills it's building along the way.
So we can't anticipate the risks.
How do you prepare for the fact that the very next threshold of scale might unlock a dangerous ability no one predicted, emerging from the exact same mathematical process that gave us a poetry translator?
That is deeply unsettling, especially since the field historically assumed this wouldn't happen. The essay points out that before these massive models, the dominant assumption in computer science was that scaling would eventually hit a ceiling.
Yeah, they thought it would level off.
Experts thought you would get diminishing returns, that making a model 10 times larger wouldn't make it 10 times smarter.
But the empirical evidence proved those ceilings simply did not exist. More computing power produced more complex internal representations of the world, and those better representations unlocked entirely new capabilities.
So there's no ceiling in sight.
The lesson researchers learned was humbling. Keep scaling, keep watching, and absolutely do not assume you know what the next threshold will reveal.
So to sum up this incredible journey we've just been on, we started with the surreal image of a calculator spontaneously translating French poetry.
Which is still a great image.
From there, we uncovered the very real mystery of AI models learning to code and do math simply by trying to guess the next word in a sentence. We looked at steam engines powering the world before thermodynamics existed. We explored the physics of water turning to ice. We visualized the invisible neural progress of a child learning to read. And we navigated the intense scientific debate over whether our own pass-fail benchmarks are tricking us.
It is a powerful reminder of how much of modern science is still driven by sheer observation. We're basically building the ship as we sail it.
We really are. And for you listening, the next time you open an app and interact with an AI, remember this. You aren't just using a standard, intentionally designed tool. You are interacting with an uncharted map.
I like that phrasing.
The capabilities of the system you're using are still being discovered, not just designed. And if you are someone who craves the hardcore, under-the-hood explanations, Aaron Rose's Part 4 promises to dive into the heavy math information theory, representation, geometry behind all this magic.
Which leaves us with one final vital question, building directly on that debate about our measurement instruments.
What's that?
Well, if our benchmarks, the prompts and tests we write, are currently the only way we discover these undesigned capabilities, what happens when these models become so complex that we don't even know which benchmarks to write?
Oh, wow.
What hidden alien capabilities might already exist in the models you're using right now, simply sitting dormant, because no human has typed the exact right prompt to trigger them?
That is a thought that is going to keep me up tonight. The idea that the AI on my phone right now might have profound abilities we haven't even stumbled upon yet, just waiting for the right sequence of words to wake them up. Thank you so much for joining us on this deep dive into the capabilities nobody designed. Until next time, keep questioning the tools you use and keep exploring the uncharted maps.